Faraday's law implies that a changing magnetic flux through a circuit produces an induced EMF in the circuit. As we've seen in our discussion of electromagnetic induction, this changing magnetic flux can result from many factors. For example, the magnitude of the magnetic field within the circuit can change in time, or the direction of the magnetic field within the circuit can change in time, or even the circuit area can change in time. For the special but important case when this changing magnetic flux is caused by a changing current within the circuit itself, we speak about the self-inductance of the circuit. When this changing magnetic flux is caused by a changing current in a different circuit, we then speak about the mutual inductance of the circuit. So in this video, we discuss the theory behind both mutual inductance and self-inductance, as well as applications of these phenomena.
Notice here in this demonstration we have two solenoids. We have the green solenoid on the left, which is connected to a power source, a DC power source. And we have a non-powered solenoid on the right, this red solenoid, this red coil, which is connected to an ammeter. So should any current be generated in it, we can get an ammeter reading. So the first thing we're going to look at is what happens when we increase the current in the powered solenoid. Okay, take a look at the ammeter here. Notice that we generate a small but noticeable current while the voltage is changing. Okay. While in the first demo we increased the current in the powered solenoid, this time we're going to decrease the current in the powered solenoid. Take a look at the ammeter. So in this next demonstration, we're going to change the position of the solenoids with respect to each other. I'm going to move this powered solenoid further away from the non-powered solenoid. We'll go through the same process, okay, and see what happens to the current generated. So I'm going to gradually increase the current on the powered solenoid. So you'll notice in this case, we have interchanged the two solenoids. So the green solenoid, which was initially connected to power, is now non-powered, is connected to the ammeter, whereas the red solenoid that was connected to the ammeter is now connected to power. Let's go through the same process and see how that affects the current generated in the non-powered solenoid. I'm going to gradually increase the current in the red solenoid. You'll notice in this last demonstration that we've inserted an iron rod in the interior of both of these solenoids, which has the effect of linking their fluxes. Notice what happens to the current, okay, in the non-powered solenoid when we increase the current in the powered solenoid.
Okay, so let's summarize the results from the demonstration that you just witnessed. So here is a schematic of our setup, and you'll notice once again that we have two solenoids. Okay, they can certainly have different numbers of turns. Notice that one solenoid, what I'm calling solenoid 1, is connected to a power source. We'll call that the powered solenoid, whereas the other solenoid, solenoid 2, is non-powered. It is not connected to a power source, but it is connected to an ammeter to measure any current that gets generated. So let's review what we observed in the demonstration. Recall that when we gradually increase the current in the powered solenoid in solenoid 1, this had the effect of creating a current in the other solenoid, solenoid 2, the non-powered solenoid, and that current had a specific direction. When we gradually decrease the current in our powered solenoid, what effect did this have on the non-powered solenoid? Okay, it also created a current in the non-powered solenoid, but in this case in the opposite direction. We also took a look at what was the effect of changing the arrangement of the two solenoids, of the two coils, with respect to each other. In other words, changing their location near each other as well as their orientation. And we noticed that this definitely had an effect on the current in the non-powered solenoid, the current that was generated in the non-powered solenoid. So the arrangement of the coils with respect to each other, that is their location orientation, certainly affects the size of the current generated. We also took a look at what would happen if we interchange the two coils, the two solenoids, so that what started out as our powered coil became the non-powered coil, and what started out as our non-powered coil became the powered coil. And what we noticed is that it had absolutely no effect on the current that was generated in the non-powered solenoid. And finally, we looked at the effect of linking the solenoids, linking the magnetic flux by introducing an iron core that penetrated both solenoid interiors. And we saw that the effect was dramatic, that when we can link their fluxes together, this had a dramatic increase in the current in the non-powered coil.
So what you've witnessed in this demonstration involving two solenoids whose magnetic field lines are linked is what we call mutual inductance. As we'll see a little later, this is the theory behind transformers. So let's start here by describing the theory behind what you witnessed. So we're going to take a look at this flow chart, and we're going to say here that we started with a current in the powered solenoid, and as we well know, that current in the powered solenoid will create a magnetic field in the interior of that powered solenoid. Now, so long as the magnetic field lines of the powered solenoid are linked to the non-powered solenoid, we can then say that, the magnetic field in the powered solenoid will create a magnetic flux through the non-powered solenoid. So, given what we see in this flow chart here involving these two solenoids, we want to now take a look at what happens when we take the time rate of change of these quantities. So starting here with the current, we say I1 in the powered solenoid. When we take the time rate of change of that current, we see that the changing current in the powered solenoid will lead to a changing magnetic field in the powered solenoid. And due to the flux linkage with a non-powered solenoid, that changing magnetic field in the powered solenoid will now lead to a changing magnetic flux in the non-powered solenoid. And as we know from Faraday's law, that changing magnetic flux in the non-powered solenoid will lead to an induced EMF, an induced current in the non-powered solenoid. So basically, the end result here, what we can say in conclusion, is that a changing current in the powered solenoid will lead to an induced current in the non-powered solenoid. This is what we mean by mutual inductance. This animated GIF nicely illustrates what we've stated in the flow chart, that an alternating or changing current in the powered solenoid produces a changing magnetic field in the powered solenoid, and that when a second non-powered solenoid is brought near the powered solenoid, allowing the changing magnetic field of the powered solenoid to penetrate its interior, a current gets generated or induced in the non-powered solenoid. So what sort of factors will affect the magnetic flux through the non-powered coil? Certainly the amount of current in the powered coil okay, will affect the strength of the magnetic field in the powered coil, okay, which will ultimately affect the magnetic flux through the non-powered coil. The geometry of the coils also matters. Okay, the number of turns of wire in each coil, as well as the cross-sectional area of the coils, will have an effect on the magnetic flux through the non-powered coil. And finally, the arrangement of the coils with respect to one another, okay, that is the distance of the coils from one another as well as their orientation with respect to one another, will also affect the magnetic flux through the non-powered coil. So we're now in a position to introduce this new physical quantity that we call mutual inductance. As we said in the previous slide, a current in the powered coil generates a magnetic flux through the non-powered coil. And the mutual inductance is simply the proportionality constant between these two quantities. That is, the proportionality constant between the current in the powered coil and the magnetic flux through the non-powered coil. Now, I've said that it doesn't matter which coil is powered. So essentially, we can say that the mutual inductance is simply the proportionality constant between the current in one coil and the total magnetic flux through the other coil. So we can define it as follows. We use the symbol capital M to represent mutual inductance. And here we're saying it's really the ratio of the total magnetic flux through the non-powered coil divided by the current in the powered coil. Or since it doesn't matter which coil is powered, we can say it is the total magnetic flux through one coil divided by the current that exists in the other coil. Qualitatively, we can interpret mutual inductance as follows. Well, this is pretty much a restatement of what we already said. We can think of it as a proportionality constant between the current in one coil and the flux through the other coil that characterizes the geometry and arrangement of the two coils. Now, there is another interpretation, which we're going to introduce in greater detail in this next slide, that involves Faraday's law of induction. And this will make more sense when we look at the mathematics here, but we can also say that, or think of the mutual inductance as being that proportionality constant between the induced EMF in one coil and the given rate of change of the current in the other coil. I want to note here, that since the value of M, the value of the mutual inductance depends only upon the geometry and arrangement of the coils, it makes no difference whether the current exists in coil 1 or coil 2. That regardless of which coil is the powered one or the non-powered one, the value of the mutual inductance will be exactly the same regardless. From our definition of mutual inductance, we can now derive an expression of Faraday's law for the mutual inductance of these two solenoids. So starting with what we introduced on the previous slide, we said that the mutual inductance is simply the proportionality constant between the total flux in the non-powered coil and the total current in the powered coil. So that's what we see here in this first line. When we take the time derivative of both sides of this equation to get the time rate of change of these quantities, that brings us to our second line right here. And you'll notice here when we take a look at the left-hand side of this equation, that this represents the time rate of change of the total flux through the non-powered coil. And according to Faraday's law, this is simply the magnitude of the induced EMF in the non-powered coil. With the exception of the minus sign here, which as we know is really what we refer to as Lenz's law. We see here that the left-hand side, with the exception of that minus sign, represents the induced EMF in that non-powered coil. And so when we multiply both sides by -1, okay, we end up with this result that the induced EMF in the non-powered coil, okay, is equal to the opposite of this proportionality constant, mutual inductance, times the time rate of change of the current in the powered coil. So, as we said, since it really makes no difference which of these two coils is the powered one, okay, whether it's coil 1 or coil 2, we can equally say then that the induced EMF in the other coil, let's say coil 1, is, okay, equal to this proportionality constant times the time rate of change of the current in the other coil, okay, in this case coil 2. And as I've said many times here, okay, the EMF induced in one coil, okay, is directly proportional to the rate at which the current in the other coil is changing. Okay, that's what this equation tells us. And that the value of that mutual inductance and induced EMF does not depend upon which of the coils is a powered one. That is, which of the coil draws the current. So, as you might expect, with our definition of this new physical quantity we call mutual inductance, comes a new unit. So we start with our definition of M, right? This proportionality constant between the flux through one coil and the current in the other coil. And given what we know about units for magnetic flux, right? The magnetic flux is measured in Tesla meters squared. It's a measure of magnetic field strength times area. And we divide that by a current, which the SI unit is the ampere. So a Tesla meter squared per ampere is what we call 1 Henry, named after the great American physicist Joseph Henry. Okay, and we symbolize the Henry with a capital H. Okay, from our expression for mutual inductance using Faraday's law, okay, we see it's a proportionality constant between the EMF induced in one coil and the time rate of change of current in the other coil. And when we look at the magnitude of this unit expressed in terms of these quantities, okay, we solve the equation for M, we see that it goes like a measure of, okay, EMF times the reciprocal of the time rate of change of current. When we plug in our SI units here, we see here that the EMF, okay, here is measured in units of volts. Okay, dt, this time differential having the SI unit of second, and once again current here being in amperes. Okay, we see that a volt second per ampere, okay, is also what we call 1 Henry. So Henry is the unit we use for mutual inductance, as we will see when we talk about self-inductance later on in this presentation. Okay, it is equivalently the unit we use for self-inductance as well.
All right, so let's take a look at some common applications of mutual induction, starting with pacemakers placed inside the human body very near the human heart. You can imagine that in the case of a pacemaker, mutual induction can allow for a coil placed externally outside of the human body to power and transmit energy into the coil in the pacemaker itself that's placed inside the human body with no direct electrical connection. You can see here that the changing current in the powered coil outside of the body, okay, will transmit a changing magnetic flux through the non-powered coil inside the human body near the heart, and activating that pacemaker when necessary. The big advantage is that no surgery is required to actually replace the batteries inside the pacemaker. So you'll see this same technology used in wireless battery chargers, whether Okay, you've got a wireless battery inside your electric toothbrush or inside your smartphone, as the simulation shows. You can see here the big advantage is that energy can get transferred via mutual induction. The coils in the base unit are going to be connected to an external AC power source, and that alternating current from the power source will provide a changing magnetic flux through the non-powered coil in the device itself. Okay, and that changing magnetic flux will induce a current in that coil to make the device operate. Once again, big advantage, no direct electrical connection is required, okay, to the actual device. Spark plugs become another example of mutual inductance in action. So the electric sparks that are needed to ignite the gasoline air mixture in the internal combustion engine, okay, are provided by the car's ignition coil. Now, the ignition coil, as you can see in the diagram, is really an arrangement of two different coils. One coil with a lot of turns, okay, that is what we call the primary coil, surrounding a secondary coil, okay, with a lot more turns. So when current from the car's battery, and we can trace this here, when current from the car's battery reaches that primary coil, the red coil in the diagram here, that current is interrupted at regular intervals by a switch in the car's distributor. And this sudden change in current in that primary coil will induce a large EMF, okay, in the coil with more turns. That is the secondary coil. And this large voltage then will be, okay, impressed across the spark plug gap to provide the large spark that is needed to ignite, okay, the mixture of fuel and oxygen. And lastly, we'll take a look at the case of transformers in a future slide. All right, so we've looked at some applications of mutual induction from a qualitative point of view. Let's take a look at a slightly more quantitative example. And in this case here, we're told that a two-turn coil is wrapped around a long solenoid with cross-sectional area given by 25 square centimeters, okay, with 3,000 turns per unit length. We're asked to find the mutual inductance of this coil arrangement. And as we've said previously and repeatedly, when we have an arrangement of two coils, it makes no difference which we consider to be the powered coil or the non-powered coil. So we're going to start by noting that if we have an ideal solenoid, the solenoid field is uniform in the interior of the solenoid and it is confined to that solenoid interior. In other words, we can assume that there is no magnetic field exterior to that solenoid. Why this is important is because that tells us that the flux of the solenoid field through the two-turn coil is restricted to an area exactly equal to that of the solenoid, since we are assuming that there is no field outside of that solenoid. So, in other words, we can then say that the flux, the magnetic flux through the coil, is due to the magnetic field created by the solenoid that penetrates the coil. And you'll notice that the solenoid field penetrates in a direction that is perpendicular to the plane of the two-turn coil. Okay, so our cosine theta factor is really 1. And as we just said, the area of the solenoid, okay, would be used to calculate the flux through the coil, since there is no magnetic field outside of that solenoid area. And when we plug in our expression for the magnetic field of a solenoid, okay, we end up with this expression for the flux of the coil. We can now use our definition of mutual inductance, okay, which is simply this ratio of the total flux through one coil divided by the current in the other coil. And as we said, it makes no difference which coil we consider, but since we've found the flux through the two-turn coil here, okay, let's go ahead and keep that in our numerator. So we're going to take the number of turns of coil times, okay, the flux through the coil divided by the current of the solenoid. Okay, so we'll let the two-turn coil represent the quantities in our numerator and the solenoid the quantities in our denominator. And when we plug in this expression here for the flux of the coil, okay, when we plug that in here, okay, we end up with, okay, this expression here. And you'll notice that the current that exists in the solenoid I put in red, so you can see that that solenoid current cancels out, okay, from numerator and denominator, in which case, okay, we can write our expression for mutual inductance as the product of these four factors, right? The number of turns of our coil times the permeability constant times the number of turns per unit length of the solenoid times the cross-sectional area of the solenoid. When we plug in the numbers here, we have a two-turn coil, so plug in the value of 2 for big N, plug in the value of the permeability constant. Okay, the solenoid, the number of turns per length is 3,000 turns per meter, and we will plug in the cross-sectional area of the solenoid after we convert it to square meters, okay, from square centimeters to square meters. And when we do the number crunching, we find out we get this very small number, okay, 19 times 10 to the minus 6 henries, which is about equal to 19 microhenries. So a henry is a rather big unit of inductance. We'll point out here once again that the value of mutual inductance depends only upon the geometry of the coils, okay, not on the current. You see that the current cancels out, so that proportionality constant, mutual inductance, has zero dependence, has no dependence on, okay, which coil is powered or even whether or not, okay, there is any power to a given coil. It depends only upon the geometry and the arrangement of those two coils. All right, so a primary application of mutual inductance that we mentioned in a previous slide but really haven't discussed in any great detail is that of the transformer. The transformer is a device for changing the voltage. In other words, it's a device for which you put in a voltage and it provides a different output voltage. As you might imagine, there are really two types of transformers. There's what we call a step-up transformer and a step-down transformer. In a step-up transformer, this type of transformer provides a greater voltage out of the device than you would put into the device. Some examples, well, maybe not so much anymore, but okay, TV sets that were based on CRT, cathode ray tube technology, required a high voltage to operate. So within every TV set would be a transformer because the typical 110 volt voltage supplied by a typical US electrical outlet was insufficient to operate the CRT. We also mentioned the example of power transmission, that in this country we want to transmit power at high voltage, low current in order to reduce the I²R power loss. Okay, this greatly increases the efficiency with which electrical power can be transmitted over long distances. So a step-up transformer would be needed in that case. The electrical power has a certain voltage that is produced at the generator at the power plant, but very nearby will be a large transformer to be able to step up that voltage to several 100,000 volts typically before it gets transmitted from the power company, okay, into the cities. A step-down transformer does exactly the opposite. Okay, it is a device that provides a smaller voltage out, okay, than is put into the machine, into the device. So, for example, electronic devices that have become so popular in today's society usually operate on much lower voltages. You may need a rectifier to be able to convert the AC voltage into the AC current into a DC current, but you certainly are going to have to step down the voltage from, the 110 to 120 volt electrical outlet, okay, to a more usable device voltage somewhere on the order typically of 12 volts or less. So this is very often done with a converter, okay, but in in some cases this is accomplished with a step-down transformer. And as we're talking about power transmission above, you may need to step up the voltage from the generator, okay, to the transmission lines, but once that electrical energy makes its way into the cities, into the neighborhoods, okay, where the homes are, that voltage is going to have to be stepped down, so you're going to need a step-down transformer there. And very often when you look at the utility poles, you see these very large garbage can looking devices high up on the pole. These are the transformers for stepping down, okay, the voltage to a more acceptable 220 volt level. So this question that Bongo is asking us, this question for reflection here, why won't a transformer work with a DC power source? Okay, we'll see in a future slide. All right, so in answer to the question, how do transformers work? Okay, the answer is very simple. Okay, none other than the principle of mutual inductance that we've been talking about in the presentation thus far. So if we look at a schematic of a transformer, you'll see that it consists of two coils, a primary coil and a secondary coil. The primary coil is the powered coil, okay, which is connected to your AC power supply. The secondary coil provides the output voltage, and you will notice that running in the middle of both of these coils is a laminated soft iron core. The purpose of that is to link the magnetic flux of the primary coil with the secondary coil. We want as many of those magnetic field lines as possible, okay, generated in the primary coil to actually penetrate that secondary coil. So as we said, the principle of operation is, there is nothing new here. It's the principle of mutual inductance. So an AC current, an alternating current in the primary coil produces a changing magnetic field in the primary coil. And in answer to Bongo's question on the previous slide, you can see that without an alternating current in the primary coil, if you had a DC current, for example, you might produce a magnetic field in that primary coil, but if that magnetic field does not change, then according to Faraday's law of induction, okay, you do not induce an EMF or a current in the secondary coil. So having that AC current is very important. So anyways, that changing current in the primary coil, which produces the changing magnetic field in the primary coil, since that primary coil is linked to the secondary coil through this iron core, that changing magnetic field in the primary coil produces a changing magnetic flux in the secondary coil. And according to Faraday's law of electromagnetic induction, that changing magnetic flux in the secondary coil gives rise to an induced EMF, an induced current in the secondary coil, which can be used to drive a current in an external device. As we said previously, the purpose of that iron core is to guide the flux. It ensures that all of those magnetic field lines, okay, that are generated in the primary coil are transferred efficiently to the secondary coil. So the question here is posed, why are transformers often very heavy? Well, you can imagine that that laminated soft iron core is quite heavy. And transformers tend to be clunky devices. They tend to be somewhat immobile because of those laminated soft iron cores add a lot of weight to the device.
The transformer equation describes the very simple yet important relationship between the input and output transformer voltages and the number of turns in both the primary and secondary coils. So in this slide we will derive this important equation. So we start with Faraday's law of electromagnetic induction and apply Faraday's law to both the primary and secondary coil. And we will start here with the primary coil. So according to Faraday's law, we can say that the input voltage at the primary coil, okay, which is caused by this alternating current, okay, our AC power source here, that input voltage must be equal in magnitude to the time rate of change, okay, of magnetic flux in the primary coil. In other words, that input voltage, okay, is exactly equal in magnitude to the rate at which the magnetic flux is changing in that primary coil. When we apply Faraday's law to the secondary coil, now remember the secondary coil, the voltage is being induced, okay, due to the flux linkage with the primary coil, right? So we're inducing a voltage, inducing a current, but again, we can say that that induced voltage, the induced EMF in the secondary coil, okay, has a magnitude equal to the rate at which the magnetic flux is changing in that secondary coil. Now, another assumption that we make in an ideal transformer, and that's where we make this assumption to come up with this equation. One of the assumptions we make is that we have perfect flux linkage. In other words, all of those magnetic field lines that are generated in the primary coil, okay, are linked through the soft iron laminated core to the secondary coil. Okay, so all the magnetic field lines in one coil must penetrate the other coil. And this is what we mean by perfect flux linkage. In which case, we can say the rate of change in magnetic flux through that primary coil must be exactly equal to the rate of change of magnetic flux in the secondary coil if there is perfect flux linkage. We also make another assumption. Okay, since magnetic energy is stored in the magnetic field, okay, created in the solenoid, we are assuming that this magnetic energy is exactly transferred from primary to secondary. Okay, that there is no energy being converted or lost in the form of thermal energy. Now, we know that for real transformers, this is not true. Okay, that's why when you touch a real transformer, they heat up. Some of that magnetic potential energy does get converted into thermal energy. Okay, so that not all of that magnetic potential energy is transferred from one coil to another. But, we assume that in the ideal transformer, okay, there is no energy conversion into thermal energy. And for real transformers, for most cases, this tends to be fairly small. So given that, we now can, and given the fact that we said that we have perfect flux linkage, so the rate of change of magnetic flux in one coil is identical to the other coil, okay, we can simply do a little bit of algebra here, okay, and when we solve the primary coil for time rate of change of magnetic flux and do the same for the secondary coil, okay, we see here that we come up with this equation, right? The time rate of change of magnetic flux in the primary coil is equal to this ratio of voltage in the primary coil divided by the number of turns in the primary coil, And similarly for the secondary coil, the time rate of change of magnetic flux there is exactly equal to this ratio of voltage induced in the secondary coil divided by the number of turns in the secondary coil. We can rearrange this equation if we like, okay, and this is more commonly the way the transformer equation is expressed. So you'll notice here that what this tells you is that the ratio of the output voltage in the secondary coil to the input voltage in the primary coil is exactly identical to the ratio of the number of turns in the secondary coil to the number of turns in the primary coil. So you can see very simply from the transformer equation that in the case of the step-up transformer, where you end up with a greater voltage out of the transformer than you put in, this is very simply accomplished by having a greater number of turns in the secondary coil than in the primary coil. So, for example, if you want to get twice the voltage out of the device as you put in, okay, then you need to have twice the number of turns in the secondary or output coil as you have in the primary coil. Similarly, we can say that in the case of the step-down transformer, where you're trying to reduce the voltage, okay, getting a smaller voltage out than you put in, okay, then the opposite would be true. Okay, that is that the number of turns in the secondary coil must be less than the number of turns in the primary coil.
So here we have an example of a transformer. You'll notice that it consists of two sets of coils. The coil on the left is connected to a power source here. It's what we call the primary coil. And this voltmeter on the left is registering the input voltage on the primary coil. The coil on the right here is what we call the secondary coil. It's not a powered coil, okay, but it is connected to this voltmeter over here. And you'll notice also that these two coils, their fluxes are linked via this ferromagnetic core, which penetrates the interior of both coils. The primary coil on the left has 400 turns. The secondary coil on the right has 800 turns, twice as many turns. Notice what happens with the voltages. The input voltage on the primary coil is about 4.2 volts here. Yet, if you look at the output voltage, okay, it's generating a voltage, okay, of about 7.94 volts, almost twice, okay, as many volts, okay, on the secondary coil as the primary coil. This, therefore, is an example of a step-up transformer. By having a greater number of turns in the secondary coil, okay, we have a greater output voltage than input voltage. Now you'll notice in this setup, if you're very observant, that we have interchanged the two coils. So you'll notice that the red coil on the left, which has a greater number of turns, the 800 turn coil, is now connected to our power source over here. It becomes the primary coil, whereas the coil with a fewer number of turns, our 400 turn coil over here, is now our secondary coil, providing us an output voltage. You'll notice that for an input AC voltage of 4 volts here into the primary coil, this transformer is generating an output voltage that is significantly less, an AC output voltage of only about 1.8 volts. So this is characteristic of a step-down transformer. When your primary coil has a greater number of turns than your secondary coil, okay, your output voltage at the secondary is going to be less than your input voltage at the primary. So I want you to notice in this demonstration that we still have our transformer. Okay, we still have the step-down transformer setup, but you'll notice that in this case, I've connected the primary coil to a DC power source. Okay, and the DC power source is supplying a DC voltage here of about 3.1 volts. And what I want you to notice is that there is no output voltage on that secondary coil. Okay, if you do not have a changing voltage on the primary from an AC power source, a transformer is not going to generate any output voltage or output current. The transformer is not going to work.
All right, so let's take a look at a specific example where we use the transformer equation. In this example, we're told that we need to design a transformer that could be used to run a US-made device in Western Europe, where the voltage supplied by the electrical outlets is about 220 volts, about twice that of what it is in this country. Describe what this transformer would look like with regards to the number of turns of wire in the primary and secondary coils. So taking a look at what we're given here, we're given that the input voltage from the wall outlets in Western Europe, okay, which represents the voltage of the primary coil, is 220 volts, while what we desire for an output voltage to run our device, a device voltage in the secondary coil, would be 110 volts, because this device is made to run in the United States, where it would require a voltage of about 110 volts. So using our transformer equation, we can see that we would need a step-down transformer, needed in this problem to step the voltage down from an input voltage of 220 volts to an output voltage of 110 volts. The transformer equation looks like this. When we plug in the given information, our output or secondary voltage of 110, input or primary voltage of 220. And just solving, rearranging this equation, this tells us that the transformer design would be as follows, that the number of turns of the primary coil must be twice as many as that of the secondary coil. We would need to have twice as many turns in the primary coil as the secondary coil to achieve or create such a transformer.
So in looking what our little friend here has to say, it sure seems like we're getting something for nothing. Think about the case of the step-up transformer, where we can get more voltage out of the device than we put into the device. How is this possible? Remember that voltage is a measure of electric potential energy per unit charge. And you know that you're never going to get more energy out of a system than you put into it. That would violate this fundamental law of conservation of energy. So let's take a look and see what the law of conservation of energy has to say about this. And we'll start by taking a look at the case of the ideal transformer, where we said that we have, in addition to the perfect flux linkage, we also have 100% efficient electrical energy conversion, producing no heat. So in other words, the energy that is input in the form of the AC current at the primary coil, all of that electrical energy, or I should say none of that electrical energy is converted into thermal energy, and creating that induced EMF in the secondary coil. So with that said, and we know, I want to stress again that this is for the case of the ideal transformer. This is the assumption that we make, that perfect flux linkage, no electrical energy loss. That would mean that the transformers would not heat up. But when we make this assumption, we can then say that the power that is being input into the primary coil must be exactly equal to the power that we are getting out of the secondary coil. So given that, and given our definition of electrical power, which goes like current times voltage, we can say that the current, the alternating current in the primary coil times the voltage of the primary coil must be exactly equal to the induced current in the secondary coil times the output voltage of the secondary coil. And when we rearrange this equation, writing it like this, we see that we have this rather interesting conclusion here. What we can see is that if that voltage gets increased by a factor X, and this is the case of the step-up transformer, then we can say that the current in our output secondary coil must get decreased by the same factor X. So in this case here, we're not getting any more power out than we put in. True, you can make a trade-off. You can get more voltage out than you put in, but this comes at the expense of getting less current out than you put in. So this is how we can see that we are not violating the law of conservation of energy here. Just want to point out, remember what we said previously about the case of electrical power transmission. We said that AC power transmission has the big advantage over DC because of the fact that voltage can be stepped up or down with transformers. Okay, this is not the case of DC power transmission. So that when transmitting power with AC, okay, the above equation tells us that we can basically trade off voltage for current. So transmitting electrical energy at a high voltage and low current has the effect of reducing that inherent I squared R power loss, which is the loss of useful electrical energy to the form of thermal energy. So that is why the voltage will be stepped up at the power plant via large transformers and then transmitted over large distance, most of the distance to the neighborhoods at high voltage and low current. And then that voltage is stepped down with transformers, closer to the people's homes. Okay, so you see in the picture over here that these garbage can looking devices on the utility poles are really the transformers required to step the voltage down from tens of thousands of volts to the voltage needed, the hundreds of volts needed in the neighborhoods themselves.
So we're now going to shift our attention from the phenomenon of mutual inductance to a related phenomenon known as self-inductance. As we'll see, many of the concepts we introduced in this lesson to describe the mutual inductance of two coils can be applied to similarly explain the self-inductance of a single coil. So let's start by reviewing what we said about mutual inductance and then see the parallels to this new quantity called self-inductance. So reviewing what we said previously about the cause of mutual inductance, we said that given two coils, if we have a changing current in our powered coil or solenoid, this has the effect of producing a changing magnetic field in the powered coil or solenoid, which when linked to a different solenoid or coil, a non-powered one, will produce a changing magnetic flux in that other solenoid, which according to Faraday's law of induction will then induce an EMF and induce a current in that non-powered coil or solenoid. So in the case of mutual inductance, we see how a changing current in one solenoid will produce a current in a second solenoid. When we take a look at the case of self-inductance, we really start at the same place, being that we have a single coil in this case, and that a changing current in that single solenoid or coil, just like in the case of mutual inductance, will produce a changing magnetic field in that single solenoid or coil. But now that changing magnetic field will also produce a changing magnetic flux in the same coil or solenoid, which will induce an EMF and induce a current in that same coil or solenoid. So if we speak in general of inductance as being the phenomenon whereby an EMF and current is induced as a result of a changing current in a coil, Okay, we see that while a changing current in a given coil can induce an EMF in a different coil, this is what we consider to be mutual inductance. We also see that a changing current in a given coil can also produce an induced EMF and current in the same coil. Note that this is really nothing more than the back EMF that we mentioned in the motor overload example in a previous lesson. So, according to Faraday's law, this induced EMF in the same coil for which the current changes in time is in a direction which opposes the change in flux that created it. Said a little differently, this induced current will be in a direction so as to oppose the changes in source current, okay, that created it. Our discussion from the previous slide in taking a look at a specific example to see the direction of the induced current and a current that gets induced in a circuit when the source current changes. So in this example, we're asked to consider a circular loop carrying a counterclockwise current. Note the direction of the magnetic field line. So when you look at the picture, remember that we use the right hand rule by placing the thumb of our right hand in the direction of the conventional current, and we see that our fingers will point in the interior in the loop in the direction of the magnetic field. And we're going to consider how changing the source current will induce a back EMF and back current in the loop, and we're asked to find, what is the direction of this back current that gets induced with the particular changes in source current. So looking at all possibilities here, let's start by considering the case where we have an increase in the source current. So you'll remember that as the source current increases, this is going to cause an increase in magnetic flux in the interior of that loop. And according to Lenz's law, a change in the source current will induce a magnetic field and will induce a current that opposes the change in source current that created it. So if increasing the source current in the loop causes an increase in magnetic flux, we can then reason that the direction of the induced magnetic field needed to oppose the change in flux must be in the opposite direction to the original magnetic field. So if the original magnetic field is upwards, okay, then the induced magnetic field must be downwards in order to oppose that change, in which case, once we know the direction of the induced field, we can once again use our right-hand rule to determine the direction of the induced current, which for this loop will be in a clockwise direction. It will be opposite the direction of the source current. Likewise, when we look at the opposite change, that is when the current decreases, we see that this corresponds to a decrease in magnetic flux in the interior of the loop. And in this case, the direction of the induced field needed to oppose that change in flux, the induced field must be in the same direction as the original field to oppose that change. And once again, using our right-hand rule, we see that this corresponds, okay, to the case where the induced current will be counterclockwise, that is in the same direction as the source current. So in conclusion, we see here that the direction of the induced EMF and induced current will always oppose the change in source current that created it. In other words, the induced current is such that it tries to maintain the source current. We see that the system, in this case a circuit, will respond to any changes in source current by trying to prevent those changes. For those of you chemists out there, you might see the natural parallel between Lenz's law and Le Chatelier's principle. Le Chatelier's principle states that when stressing a system in chemical equilibrium, perhaps by changing the concentration of a given reactant or product, or by changing the pressure or temperature of the system, that the system will respond by trying to reduce or eliminate the stress. In a similar fashion, when the source current in a circuit is changed, we find out here in this example that the system will respond by inducing a current in a direction that opposes a change in source current, in effect trying to maintain the source current status quo.
In this slide, let's formally define this concept that we call self-inductance. And we will symbolize the self-inductance of a solenoid or coil with the symbol capital L. So qualitatively speaking, we can think of self-inductance as being a property of a circuit whereby its own magnetic field opposes changes in current. And we'll talk more about this when we talk about the function of an inductor in a circuit. We can also think of the self-inductance as simply the proportionality constant between the magnetic flux through the circuit and the source current in the circuit. If we think back to our discussion of mutual inductance, we similarly said that the mutual inductance was simply the proportionality constant between the current in one coil and the total flux generated in the other coil. Of course, here for self-inductance, we have only one coil, so quantitatively we think of it as a proportionality constant between the current in that coil and the total flux in that same coil. When it comes to units, okay, well, whether we're talking about mutual inductance, it's a ratio of flux to current. Same for self-inductance, so we would expect that the unit, the Henry, okay, would similarly be an appropriate unit for self-inductance in the same way we introduced it for mutual inductance.
All right, so let's now take a look at a specific example where we calculate the self-inductance, or commonly just referred to as the inductance of a solenoid. So we're asked to derive an expression for the inductance of a uniformly wound air-filled solenoid consisting of N turns, length L. We're asked to assume that the solenoid length is much longer than the radius of the windings, so that the magnetic field inside the solenoid can be considered uniform and, in a sense, will be parallel to the solenoid axis. So we start here by reviewing the magnetic field for a solenoid. Okay, has this expression that we've derived previously, and little n, the number of turns per unit length. Okay, in this problem we're told the total number of turns, big N, and the length L. So we will then try to calculate the magnetic flux through one turn of the solenoid using our definition of magnetic flux as this surface integral of B dot dA. Since the magnetic field is uniform and is in line with the solenoid axis, notice that it is in the same direction as dA. Remember, dA is that unit normal, which is perpendicular to the plane, okay, of the solenoid cross section here. So when we're taking the dot product, we're taking the cosine of 0 degrees, the angle between the field and that unit normal dA, in which case we come up with this expression for the flux through the solenoid. Okay, we're now in a position to plug this expression into our definition of self-inductance, right? Which is the total flux given by taking the flux through a single coil, multiplying by the total number of coils, and then dividing by the current I. When we plug in this expression we see here for the total flux through the solenoid dividing through by the current I, we see that just as in the case for mutual inductance, okay, the current ended up canceling out between numerator and denominator. Exactly the same thing happens here in the case of self-inductance, in which case our expression for the self-inductance, or commonly just called the inductance of a solenoid, is given by this expression, mu naught times the number of turns squared times the cross-sectional area of the solenoid divided by the solenoid length. Now, you'll notice here that this proportionality constant we call self-inductance depends only upon the geometry of the solenoid. Notice that it depends upon, in this case, the number of turns in the solenoid, the cross-sectional area of the solenoid, and the length of the solenoid, but in no way depends upon the current in that solenoid. Depends upon geometrical factors only.
So what we're saying here is that for any circuit within which a non-steady state current exists, any circuit where the current changes in time, such a circuit has this property of self-inductance wherein an induced current gets generated. Sometimes this induced current is significant and must be accounted for in designing a circuit, and sometimes it's not. Let's take a look at cases when self-inductance becomes important in a circuit. So in the first case applies to cases where the circuit encircles many of its own magnetic field lines. So this would be, okay, for example, the solenoid or the toroid, okay, which consists of numerous loops, meaning that, okay, a lot of the magnetic field lines generated in their interiors are encircled by these loops. A second case, okay, would be when a current changes very rapidly, such as in the case of turning a system on and off. Even in the case where you have a steady state current that is being produced, okay, that steady state current has to go from a value of 0, okay, to its steady state value when your device is turned on. And this action will produce an induced current, okay, in the circuit. Okay, what we're now going to do is we're now going to turn our attention to Faraday's law. In the same way that we derived an expression for Faraday's law that applied to the mutual inductance of two coils, okay, we will derive an expression for Faraday's law, okay, that applies to the self-inductance of a single coil. Okay, and remember that Faraday's law is a general expression that dictates when an EMF is induced in a circuit, that is, when the magnetic flux through the circuit changes in time. Inductance, you recall, refers to the special case, okay, where the induced EMF is caused specifically by a change in source current in the circuit. Okay, so we will begin our derivation exactly as we did in the case for mutual inductance. Okay, we will start with the definition, well, okay, not of mutual inductance, in this case the definition of self-inductance. So remember, you know, we said that self-inductance is this ratio of the total flux through our circuit divided by the current in the circuit. Let's multiply both sides by I, so we will see that, okay, clearly that L represents a proportionality constant between the current and the total flux in the circuit. We will now take the time derivative of both sides of the equation here, okay, and we will add in the negative sign, okay, and you will see that, okay, when we do so, on the left-hand side of our equation here, this, according to Faraday's law, is simply the total time rate of change of magnetic flux, which is exactly equal to the induced EMF in the circuit. So according to Faraday's law, okay, the left-hand side here, the time rate of change of magnetic flux in the circuit, in other words, the induced EMF in the circuit, okay, is proportional to the self-inductance of the circuit times the time rate of change of current in the circuit. So if we look at this expression and we go back and revisit the induced EMF in the case of two coils, this is in the case of mutual inductance, we see the similarity in form. Okay, then in the case of mutual inductance, of course, we're talking about two coils, and we see that the EMF induced in one coil is related to the time rate of change of the current in the other coil. Okay, but in the case of self-inductance, there's really only one coil, so we see that the EMF induced in that one coil is similarly proportional to the time rate of change of current in that one coil.
All right, so this brings us to the topic of inductors used in circuits, for which you see several examples illustrated in the right-hand corner of your screen. And if you're saying to yourself, hey, they simply look like little coils of wire with some wrapped around some sort of core, then you're exactly correct. That's all an inductor is. It's really an electronic device that is nothing more than a coil of wire, a solenoid that is designed to exhibit self-inductance. In other words, to have a specific value of self-inductance. Now, why you would want to use an inductor in a circuit? Well, the purpose of inductors in circuits are many. So let's take a look at why inductors are used, starting with perhaps the most obvious reason, which would be that if inductors exhibit self-inductance, okay, then according to what we've been talking about, putting an inductor in a circuit will oppose changes in source current through the circuit in order to help maintain a steady current in the circuit. We also may want to use an inductor in a circuit to prevent the current from changing too quickly in a circuit. Given that the circuit current is going to change, by putting in an inductor with a specific value of self-inductance, we can prevent the current from changing too quickly. A third reason for using an inductor in a circuit would be to actually control the size of the AC current in the circuit itself. To try to understand this, we'll start by taking a look at Faraday's law of induction, okay, expressed for the specific case of self-inductance. And we see here that, okay, when we look at Faraday's law, okay, we see this term here, di dt, and what this tells us is that for a given value of di dt, let's say, for example, 60 hertz, in other words, when we are talking about the current in the circuit changing at a certain rate, like let's say 60 hertz, notice that there is a direct relationship between the self-inductance and the induced EMF. But since the negative sign in Faraday's law represents a back EMF, it implies that a back EMF is being generated. This tells us that the overall voltage will be reduced, and thus the net current in the circuit will be reduced because of this back EMF. So to look at this from a slightly different perspective, let's revisit a previous discussion that we had involving electromagnetic induction, where we looked at the case of motor overload. That when the armature of a motor gets restricted from turning, the end result is that too much current exists in the motor's windings that may cause too much thermal energy to be produced and perhaps melt the circuit insulation. This happens because the back EMF, okay, cannot be generated in the circuit if the armature doesn't turn. So when the armature turns and produces a steady back EMF and induced current that opposes a source current, the net current in the circuit diminishes. The motor is designed to operate with a steady back EMF and back current so that the net current is never very big. Because self-inductance in a circuit similarly produces a back EMF and back current, okay, when this back current is added to the source current, the overall or net current in the circuit is reduced. So you see that in this way, an inductor can control the size of the overall current in the circuit. That is the net current in the circuit. And lastly, okay, we will see that inductors can be used, okay, to store magnetic potential energy. Remember that in the steady state case, inductors produce a magnetic field, okay, in their interior. And as we're going to find out in a future slide, magnetic potential energy gets stored in that magnetic field. So as with other circuit components, we have a symbol that we use to represent inductors in circuits. And it looks like this. And hopefully you agree that the symbol for an inductor, it looks like a coil of wire. So we can draw this to represent an inductor when we're drawing a circuit diagram. Let's take a look at what happens when you have an inductor in a circuit in a steady state situation. In other words, when the current isn't changing. So when the current is constant in the circuit and it does not change in time, in that case the inductor behaves simply as a coil of wire with resistance and a magnetic field inside. And as we'll see, this magnetic field will store magnetic potential energy. So we should point out that inductors can be dangerous. Okay, for circuits with large inductors, that is with large values of self-inductance, a sudden change in current could mean that di dt, the rate of change of current, is large, and according to Faraday's law, take a large rate of change of current and multiply that by a large value of self-inductance, and you end up getting a very large back EMF being generated. So the rapid switching of inductive devices such as solenoids or motors can result in circuit damage or even to the death of the individual. So while inductors are placed in a circuit to control changes in current, inductors by themselves can be dangerous. So let's revisit a case that, an example that we looked at previously, and that is, okay, the induction coil in a car's internal combustion engine. So as we said previously, as the distributor cap rotates, a contact switch continually interrupts the circuit, causing the DC current in the primary coil to be turned off and on at regular intervals. This periodic break in the circuit causes a sudden change in current and a large voltage is induced in the secondary coil. The goal is for this large voltage to be induced across the gap of the spark plug. But if for some reason the large voltage were to be induced in the gap within the switch itself, this could be dangerous to a person coming in contact with the switch. Now, the likelihood of human contact with a switch in the distributor cap may be remote, but kind of expand this idea to a circuit in general, a different circuit where a human being could come in contact with a switch, okay, for which a large voltage was induced. So let's continue this conversation about how inductors can be potentially dangerous by taking a look at a quantitative example. So in this example, we're told that a current of 5 amps is flowing in a 2 Henry inductor. In other words, an inductor with a self-inductance having a value of 2 Henries. The current is reduced steadily to 0 in a time of 1 millisecond. What is the magnitude of the back EMF in the inductor while the current is being turned off? So because current changes steadily, its time rate of change has a magnitude given by this expression, right? di dt, which is equivalent to delta I over delta t in the case of a steady change. The change in current, we're told in the problem, is 5 amps, right? Starts at a value of 5 amps and goes to 0. And this happens in a time of 1 millisecond. So if we convert that to units of seconds, this gives us a time rate of change of 5,000 amps per second. Now, when we substitute that value into Faraday's law, in other words, we multiply the time rate of change of current by the self-inductance of 2 Henries, okay, we end up with an induced EMF, okay, a back EMF of 10,000 volts. Now, this is certainly enough to produce a lethal shock. Note that this voltage is quite unrelated to the source EMF, that is the voltage of the battery or whatever else was supplying the source current. Even a 6-volt battery could lead to a lethal shock when trying to open a circuit too rapidly when a large inductance is present.
As we said previously, because inductors produce magnetic fields within their interiors, they store magnetic potential energy within this field. In this slide, we will derive an expression for the magnetic potential energy stored within the magnetic field of an inductor. So we start with an expression for the electric power within a circuit. In this case, power represents the rate at which energy is being converted from electrical energy in the form of an AC current, to magnetic potential energy, the energy stored within the magnetic field of the inductor. So we start with our familiar expression here for the electrical power within a circuit. As we see here in our familiar expression for electrical power, delta V represents the voltage drop across our inductor, which happens or is generated because of a changing current within the inductor in accordance with Faraday's law. And because of that, we will represent that voltage drop across the inductor, using the symbol script E for the induced EMF, which, as I said, results from this changing alternating current. And when we substitute Faraday's law into this expression, we're looking at the magnitude only. We see that the induced EMF goes like the self-inductance times the time rate of change of electric current. So in this case, the power represents the rate at which energy is being converted from electrical energy to magnetic potential energy. Remember way back to your course in mechanics when we initially defined the concept of power, as the rate at which work gets done. But we can here think of power as the rate at which energy is getting converted from one form into another. So in this case, as we said, electrical energy, magnetic potential energy, and we can represent the power then as the time rate of change of this energy. That is the first derivative of energy with respect to time. When we multiply both sides of this equation by dt to get rid of the time dependence, and then take the integral of both sides of the equation, from our starting value of 0, in the case of energy and both energy and current, we end up with an expression for the energy stored, within the inductor, which looks like 1/2, the self-inductance times the square of the, alternating electric current. So here, in this case, we can calculate the energy stored within the magnetic field of an inductor, which relates to the self-inductance as well as the alternating current within the circuit. Right, in this slide, we will introduce a mechanical analogy that may help you to make sense of the energy stored in an inductor as well as the meaning of self-inductance. So we're going to start with an energy comparison, that is comparing the kinetic energy of a mechanical system to the magnetic potential energy stored within an inductor in an electric circuit. So let's start by looking at the energy expressions for each. So here we have our expression for kinetic energy as well as the expression we just derived for magnetic potential energy. And when we look at these energy expressions, hopefully you can see that the expression for self-inductance here, in magnetic potential energy, has its counterpart here in the expression of mass for kinetic energy. To continue with this analogy here, we will now compare Newton's second law for mechanical systems to Faraday's law for the electrical system containing the inductor. And when you compare these two expressions here, you can once again see how inductance in Faraday's law okay, here, okay, has its mechanical counterpart in this quantity that we call mass when we're taking a look at Newton's second law. So if mass can be thought of as, okay, a measure of motional inertia, okay, that is a resistance to a change in the state of motion of an object, okay, to the change in speed of an object, okay, then we can think of self-inductance here as being a measure of electrical inertia, okay, the electrical sluggishness that is found in an inductor, okay, a resistance to having the electric current changed within that device. Okay, so we can say that, you know, as the mass increases in a mechanical system, it becomes more difficult to change the speed of an object as the motional inertia increases. Okay, in a similar fashion, we can say that, okay, as the self-inductance of an electrical circuit increases, it becomes more difficult to change the current in the circuit. So nice analogy here, okay, comparing motional inertia to the electrical inertia of a circuit.
And lastly, we'll make a comparison between magnetic energy storage and electrical energy storage in electromagnetic systems. So when we take a look at the circuit devices designed to store the energy, in the case of electric potential energy, that electronic device is the capacitor, whereas we have just been saying in this presentation that the inductor becomes the electronic device used to store magnetic potential energy. For the capacitor, the electrical energy is stored in the electric field between the charged plates of the capacitor, whereas for the inductor, that magnetic potential energy is stored within the magnetic field on the interior of that inductor. An expression for the total energy stored in the device, well, in the case of the capacitor, we say that the energy stored within that electric field between the plates goes like 1/2 the capacitance times the potential difference squared, okay, between those two charged plates. Whereas we've just now said that in the case of the inductor, okay, the energy stored in that magnetic field takes on the form of 1/2 the self-inductance times the current squared. When it comes to energy density, remember that energy density is a measure of the energy stored in the field per unit volume. And in the case of the capacitor, recall this expression, 1/2 epsilon naught, that permittivity of free space, times the magnitude of the electric field, okay, in between the capacitor plates squared. Now, we haven't derived this for the energy density of the magnetic field. Okay, I'm going to give it to you here, and okay, we can say that the energy per unit volume, okay, that is the magnetic potential energy per unit volume stored in the magnetic field, the interior of that inductor, goes like the magnetic field squared divided by 2 mu naught, the permeability of free space. Now, where that expression comes from, and this certainly won't be on the test, but I know that at this point in the presentation you're all wondering. So in that case, okay, very, very quickly show you where that comes from here. For the inductor, we said that the magnetic field can be expressed like this, okay, and from our definition of magnetic flux for a uniform solenoid or inductor, solving in our expression for magnetic field, solving that for the current, okay, we get this expression. And using our definition of self-inductance, okay, we come up with this expression that we've seen previously. So given that, we're now in a position to evaluate the energy density. So remember we said energy density, total energy stored in the field per unit volume. We said that the total energy has the form 1/2 self-inductance times current squared. Okay, divided by the volume, we'll say that's the cross-sectional area of that inductor times the inductor length. And when we substitute in the above expression for self-inductance, okay, as well as the above expression for current, and we simplify, okay, you can follow the algebra through, we come up with this expression here, B squared over 2 mu naught.